this way. Chapter, and especially for this first section of this first chapter. Because most of what we'll be looking at this, and this is kind of our objectives, representing and classifying real numbers, ordering real numbers and using inequalities, find the absolute value of a number and distance between two numbers, and evaluating algebraic expressions, and using basic rules and properties. We know what real numbers are at this point, hopefully. Real number is any number that we have except for complex numbers. And most of our complex numbers are going to come in the form of a plus bi. If I becomes a number or is a part of a number, we know it's not real. Those are the only ones that are not real. They're considered imaginary. These are our imaginary numbers. Everything else listed here and more are all going to be considered real numbers. Miles per gallons, populations, symbols, we have these here. So any of these here represent a real number. Here are some important subsets. And a subset is just a set that contains everything of another set, but does not have anything it doesn't have. So if we say that we had set A here that contained 1, 7, 14, 39, 46, if we have a subset of it, it should contain at least some of these here. Set B is 108. It's not a subset because 108 is not contained in A. If it's going to be a subset, it has to have at least some part of the other set. So these here, 1, 2, 3, 4 is a subset if 1, 2, 3, 4 is in there. Pretty straightforward so far. I think this is just rehashing some of the stuff we did in Algebra 1. So 0, 1, 2, 3, 4 is the set of whole numbers. When we add negative, it's integers. Rational is just fractions. I mean, this, I think, is the decimal representation. We can have these using bars if it is repeated. And we also have irrational numbers. That means we can't represent it as a fraction. It has a non-repeating, non-terminating decimal. So square root of 2 is irrational. Pi is irrational. It does not have a way that we can write it as a fraction. We can only approximate these. Yep, typing 0. And this is one way that we can look at it. When we looked at this in Algebra 2 at the beginning of the year, I used boxes, box and a box and a box. Because what we're saying is the real number is all of these here. All of these are considered real numbers. But the real numbers are broken into two groups. We have the irrational and rational numbers. Numbers we can't write as fractions and ones that we can. Under rational numbers, we have integers and non-integers. So integers are just our positive and negative. The non-integers are going to be considered our decimal numbers. Under integers, we have negatives and whole numbers. And under whole, we have natural and 0. And it's just ways that we can break down the numbers or think of them as their separate groups. Any questions on any of this so far? Pretty much repeat of stuff we've done before. So if we wanted to look at this group of numbers and we wanted to pick out all the ones that we would consider the natural numbers, which ones would we pick? Because how many natural numbers are up there? Well, we can say 7, yes? 7's a natural number. Any other natural numbers besides 7? I wouldn't think so. Because natural numbers are counting numbers, anything that's positive. So, and it can't have a decimal. So out of all these here, the only ones that are counting numbers and positive is just 7. Our whole numbers, well, just add 0. Whole numbers difference, only difference between whole numbers and natural numbers is 0. Well, then we can look at the integers. Well, we'll definitely have 0 and 7. But now we need to include the negatives, so that would also be -1 and -13. Because integers is just our positive and negative numbers. Now our rational numbers, we're talking about anything that can be represented as a fraction. Well, 0, 7, -1, -13, all of these would still be considered rational. But now we have to include -1/3. How's it going? Doing all right. And 5/8. Thank you. I can hear it now. Just full of, just the shut off got full for the water. Yep. Okay. Thank you. So our rationals, the only ones that we had to include was -1/3 and 5/8 because they can be represented as a fraction. But our square root of 5 and square root of 2 still aren't considered, mainly because we can't reduce it any further. Square root of 5 is irrational. Square root of 2 is irrational. So when we look at E, well, negative square root of 5 and square root of 2 are actually the only ones that are irrational. Well, besides pi, those would be the irrational ones. Now, the only reason we don't list the others is because all of these here that we listed for D are rational. These are irrational, so that's where we do have that split where we're not having them repeated again. Questions on this here? Yep, and that does agree with what we have. They do include the answers for us. I'm not going to spend much time on this here because I feel like at this point you all know how to plot numbers on a number line. Yes, negatives are always left, positives are always right. And we could go through and say, okay, well, we can demonstrate where these numbers would lie on the number line. And with irrational numbers, we can approximate what they are. So for pi, 3.14. So it's a little bit more than 3. Same thing with the square root of 2. I don't think that y'all need to see how to plot a number on a number line. I think I might have this thrown in as the homework, and if I do, most likely, if you don't, a lot of teachers, I mean, for those of you who've had me know that I don't do this, some want you to start with 0. Draw a line, start with 0, and then, okay, we can make a assignment for how it's working. You can do that if you want, but for these here, as long as they're in the correct order and somewhat spaced the way they should, we're good to go. No one's mind's blown yet. Inequality signs, because we can say something's greater than or less than a number, or equal to. And we can look at it as this here. So we can order real numbers. Well, -3 and 0, well, we know that 0 is definitely greater. Between -2 and -4, we know that -2 is bigger, because the bigger a negative number gets, the smaller it actually is. 1/4 and 1/3, it would be 1/3. 1/3's bigger. 0.3 repeated compared to 0.25. And -1/5 and -1/2, well, that would go -1/5, because -0.2 is bigger than -0.5. Feel like you're back in 8th grade math a little bit. And I mean, we could describe these subsets, because again, for this first one here, we're just saying for all values of x that are less than or equal to 2. And if I want to describe this on a number line, we can draw it here, and well, our main focus is at the point 2. Since it is equal to, we would draw a circle and fill it in and then shade everything to the left. That's all I would want in a number line. Here, we're wanting all the values of x that are between -2 and 3. Well, now we have two main points of focus, -2 and 3. At -2, since it is equal to, we will fill that in, fill the circle in, and then shade everything in the middle. And I like to do the little swirls just because it's easier to see what we're actually shading. Questions on this here? I mean, we have different sets that we can have. We can have bounded. So bounded means that there's two ends. There's a start and finish for every single one. And there's different ways we can have it. We can have it closed where we have brackets on either side. Both are filled in. Or we could have it opened, parentheses on both sides, so open circles. Or we can have it half, where one's closed and one's open, or one's open and one's closed. Or, yep, same type thing. Or unbounded. Unbounded just means that it's going to continue indefinitely in one direction or the other. And the spot that it does end is either going to be closed or open in either case. Or we could have that it's the entire line, all real numbers. Goes to infinity both directions. Go back. I don't think we need to see another example of how to write these out. No? Okay. Absolute values and distance. And this here is the definition of absolute value. The absolute value of A is equal to A if A is greater than or equal to 0. And the absolute value of A is equal to, can someone say what that is? You all know? It's very tempting to say negative A, but it's actually not considered negative A. It's actually the opposite of A. So, and that is true if A is less than 0. So if we said A is -4, which does satisfy this, yes? Well, for the absolute value, it's going to be the opposite of A. So if A is -4, the opposite of -4 is 4. That kind of makes sense. And no, I feel bad. I didn't realize that's what they were meaning till last week when I was looking at this. Because otherwise, if we think of this as negative A, that makes no sense. The absolute value of any number is always positive. But the reason they add this in is because we don't know the exact value of A. And if they just left it as A, if A is less than 0, well, that A is actually, in this case, negative. So we need the opposite of that value of whatever it is. So, like they put here, if A is equal to -5, then the absolute of -5 is equal to the opposite of -5, which is just 5. And moreover, the absolute value of 0 is always 0, because 0 is neither positive nor negative. It's actually not odd or even. We good with these here? And these are just some of the basic laws that we do have, because the absolute value of A is always going to be greater than or equal to 0. That's just always true. The absolute value of negative A is equal to the absolute value of A. They're going to be the exact same. The absolute value of A times B is equal to the absolute value of A times the absolute value of B. So we can split them apart. The same thing is true with division as long as B is not 0. As long as B is not 0, as long as we're not dividing by 0, we're good to go there. So we will look at this one here because this, again, this here is not something that you've seen. So they want us to look at two main cases. The first case is where x is greater than 0. So if x is greater than 0, by definition, the absolute value of x is going to be x. It's going to be a positive, whatever number that is. That doesn't mean anything different for the bottom one, because that's whatever the value of x is, we're going to plug it in. The only thing that we're really focused with in this first main step is this sign that's going to come out of the absolute value of x. Because if x is positive, the absolute value of positive number is still positive. And well, x divided by x is 1. Anything divided by itself is 1. So for this here, if x is greater than 0, it actually works out to be 1. Now the other condition is x is less than 0. Now by definition, the absolute value of x, if x is greater than 0, I'm talking about negatives, is going to be the opposite sign of x, or negative x. It's going to be in that sign there. But the bottom one is still just x. As we add the negative, since whatever comes out of an absolute value has to stay positive. And to account for that, we add the negative, because here both values of x are going to be negative. So we add that so to make sure that the numerator is positive after the absolute value. Well, x divided by x is still 1, but this time it is negative 1 because of the negative sign on top. Questions on this here? Nope. See if it'll scroll. Nope. All right, let's look at one more of these here, and then we'll move on. Okay. B. So we have the case where x is greater than -3 and x is less than -3. Well, what happens if x is -3? The numerator is going to become what? -3 plus 3 is 0. The denominator will also be 0, so it doesn't work as a function. We won't have a point there. But if we're talking about numbers greater than -3, what do we know is going to happen to what's inside the numerator? Is it going to be positive or negative? Well, it's going to be a positive value, yes? Because a number greater than -3 would be, say, -2. So let's use that to kind of help this make a little more sense. So we could say -2 plus 3 is on top. On bottom, it would just be -2 plus 3. Well, -2 plus 3 is 1. -2 plus 3 is 1. The absolute value of 1 is still 1 over 1, which is just 1. So it works out to be 1. But, okay, that's kind of interesting. Does it work always? I mean, we could say 3. Because 3 is definitely greater than -3, yes? So, on top we'd have the absolute value of 3 plus 3, which is going to be the absolute value of 6. On bottom, 3 plus 3 is 6. So 6 divided by 6, which is still 1. So for this here, try it again. Really, when we look at this in the kind of the general sense, the value on top is really just going to turn out to be just a positive x. And on bottom, positive x, which just works out to be 1. As odd as it seems, this actually works out to be 1. Now over here, in a similar sense, since we're talking about less than -3, what's on top of that is going to be a negative, or the opposite value of whatever x is. And on bottom, we're really just going to have that similar x value, which is just going to work out to be, well, -1. Questions on this here? Okay. I know that's a little funky. That's probably going to be the weirdest thing we come across, but otherwise, all the rest is going to be pretty easy for this section here. We can go through this here real quick because here 4 is going to be greater than 3 because the absolute value of negative 4 is going to make it positive, and that's still greater than 3. Here, these are going to be the same, negative 10. Absolute value of negative 10 is going to be the same as the absolute value of 10. And the last one, negative absolute value of negative 7, is just going to be negative 7, which is less than the absolute value of negative 7. And really, when we talk about absolute value, we're really talking about the distance between 2 points. So if we want to know the distance between 2 points, we can subtract those 2 points, those 2 numbers, and take the absolute value of it. So if we want to find the distance between negative 25 and 13, what we can do is say the absolute value of negative 25 minus 13. Negative 25 minus 13 is going to be negative 38, which gives us a distance of 38. That's it. Questions on this here? I have a whole bunch more of these, but I don't think we need to see any more of these. We're good with doing absolute values for distance. An algebraic expression is any expression that contains numbers and variables. And we have these here. And a number without a variable is considered a constant. We can deal with addition, subtraction, multiplication, and division. And the number in front of the variable is considered the coefficient. So for this here, we do have 3 terms. We have the x squared, the negative 5x, and the 8. The x squared and the 5x are considered terms with variables, and the 8 is considered a constant term. Now, we didn't deal too much with this in Algebra 2, at least I didn't talk about this too much, but the x squared term, this here is considered the quadratic term. It's considered quadratic because it has 8x to the power 2. Because when we talk about quadratic function, it means that the biggest exponent attached to the variable is a 2. So this here is considered the quadratic term. Well, this here would be considered the linear term, because if it is to the first power, it's linear. And the 8 is considered the constant term, or a constant function. Y equals 8. When we talk about a straight line, it is constant, so it's a constant term. But that's it. We can also evaluate. I didn't feel the need of walking us through this here, where we can just plug the number in for x and then simplify to figure out what it is. And at this point, especially when we start evaluating or substituting it in, we could type all that into the calculator. We don't have to do that by hand for any of these here. Questions on this so far? Substitution principle, if A is equal to B, then B can be represented. So essentially saying that we can plug in a number as long as they are equivalent. We're mainly just going to look at these here because these properties, y'all have used them time and time again. The commutative property of addition. I can add any 2 things in any order, which makes addition nice. The commutative property of multiplication. I can multiply any 2 things in any order. The associative property of addition. We can add any 3 things in any order. Same thing is true with multiplication. Distributive property. We can multiply through. Left or right side. Additive property. The additive identity property, if you add 0 to anything, you come back up with what you had originally. Multiplication, it's with 1. And most of these here that you are very familiar with. And I'm not going to bore you all with all of these properties here. Let's see here. Prime numbers is an integer that has exactly two positive factors, itself and 1, such as 2, 3, 5, 7, and 11. The numbers 4, 6, 8, 9, and 10 are composite because they can be rewritten as the product of two or more prime numbers. Questions on any of these here? Interestingly enough, you can actually take these 5 numbers here and find their factors. So 2, 4, 6, 8, 10, so on and so forth. And if you do that with the first 100 numbers, just marking off all of their factors, excluding 2, 3, 5, 7, and 11, what will be left will be the primes. So if we wrote out all the numbers between 2 and 100, or between 1 and 100, excluding 1 because 1's not prime, and marked out all of their successive numbers, the only ones left would actually be the prime numbers. It's an interesting thing, but nothing too big. Fundamental theorem of algebra states that every positive integer greater than 1 is a prime number, or it can be rewritten as a product of prime numbers. Or, sorry, fundamental theorem of arithmetic. That's it. That is all we're going to do